This is a short summary of our LIPS paper entitled The Parallel Logic Gradient Method for Batch Bayesian Optimization. This is a outline of this presentation. So basically we state the problems, propose our algorithm, how to optimize our algorithm, and the empirical performance and some future work. So the problem we care about is belong to the black box optimization broadly belong to black box optimization algorithm problem. So basically, we would like to optimize a function, and this function, the physical state of this function is regular, so it's either a box or polyhedron, and it's compact. And the function unknown function f is we assume is smooth, but if every time we evaluate f only give us a noise evaluation of the function value, then we have no information about its derivative. And the function f is typically very expensive to evaluate. So, for example, testing very complex machine learning algorithms, calibrating very complex simulators, or some even neighbor experimental design. So, for example, when trying to tune in the parameter in a complex neural nets, for example, the architecture or the learning rate in the stochastic gradient descent, it belongs to this type of problem. So the algorithm we focus on is called Batch Bayesian Optimization algorithm. We're starting from some initial design, and according to some acquisition function, we select the next batch of points to evaluate. After evaluating these points, we update the posterior of the surface. And in this work, we use Gaussian process as our stochastic surrogate model. Okay. So the parallel logic gradient has a strong decision theoretical guarantee. So basically, suppose we have observed endpoints, what is the minimum of the mean function is what we can gain if we stop long. Now, if we take one additional iteration and evaluating Q more points, we can improve our minimum of the mean. And the difference between these two functions are the information gained by observing Q more points. So basically, the QKG criterion is defined as the difference between these two minimum of the mean functions. And our QKG algorithm is trying to maximize the criteria. This is how our QKG algorithm works. So we're starting from one point, and the right-hand side is the heat map for the summarizing the QKG value. So we evaluate a pair of points, maximizing QKG vector, and continue the process. Okay, after several iterations, you can see the whole function almost is determined. And the next step of the talk is how to maximize the QKG vectors efficiently. So we are using some gradient-based optimization. So the necessary step is to get the gradient of the QKG factor. In order to get that, we're using some infinitesimal perturbation analysis to exchange the expectation and the derivative factor operator. Okay. And this is some empirical performance. So basically, our algorithm outperforms all the other Batch Bayesian optimization algorithms on noisy synthetic functions, and also it also outperforms state-of when tuning logistic regression to classify handwritten digits, and also outperforms state-of when tuning convolutional neural nets to classify images. Okay. It especially outperforms the state-of the Bayesian optimization algorithm in experiment. So we also have some future work to make Bayesian optimization algorithm scalable, to attack Bayesian optimization in high dimension, and also how to incorporate the gradients observation into Bayesian optimization algorithm.